Are you struggling to fine-tune your neural networks efficiently? Then look no further than this LoRa, DoRA, MTLoRa and adversarial because these groundbreaking approaches offer faster training times, higher performance, reduced computational cost and lower memory footprints compared to this conventional fine-tuning methods. So let's embark on this exciting journey together and unlock the full potential of LoRa, DoRA, MTLoRa and adversarial. So what is this low rank adaptation of large language model? So let me explain LoRa in a simple terms with an example. Imagine you have a pre-trained language model similar to the Google's BERT which has been trained on a large corpus of text data. Now you want to use this pre-trained model to perform a specific task such as question answering or sentiment analysis on your own dataset. So traditionally you would fine tune the entire model on this new task which require additional computing power, time and memory resource. But LoRa offers a more efficient solution. So instead of fine-tuning the entire model, LoRa will break down the weight matrices of these pre-trained models into two components, a lower rank factor matrix and a residual term. Essentially, this means that LoRa compress some parts of the model into smaller matrices that contain fewer parameters than the original ones. And then LoRa trains only those smaller matrices on the new task, leaving most of the pre-trained model unchanged. So let's understand this with the analogy. Think of the pre-trained model as a large building with lots of room containing furniture and decoration. And each room corresponds to the layer of neural network. Fine-tuning the entire model would mean moving everything around in every room to fit the new task, which may take a lot of time, efforts, and resources. So using LoRa is like renovating just a few select rooms by adding new fixtures and removing unnecessary items. You still keep most of the original structure intact, but make targeted changes to better suit the new purpose. So in practice, this LoRa reduces both the memory required to store the model and the amount of time needed to train it. It's particularly effective for very large models with the billions of parameters such as GPT-3, which previously took 2 weeks to fine-tune due to a high computational demands. So with LoRa, these models can be adapted much quicker and more efficiently, making them more accessible for real-world applications. Then comes this weight decomposed low rank adaptation. Now this DoRA, which is shortened for weight decomposed low rank adaptation, is a newly proposed parameter efficient fine tuning technique that aims to improve the learning ability of pre-trained models without introducing significant extra computational cost during inference. And it differs from this traditional PFT approaches like LoRa in that it first decomposes this pre-trained weights into their magnitude and directional components using weight normalization. Then instead of freezing most weights during fine-tuning, this DoRA adapts both the magnitude and direction simultaneously through low-rank adaptation techniques. And by using this LoRa to efficiently update the directional part of the weights, DoRA can achieve a learning capacity close to full fine-tuning without sacrificing inference efficiency. So through extensive experiments on various tasks from natural language processing to vision language benchmarks, DoRA demonstrates consistent improvements compared to LoRa, which highlights its potential as an effective alternative for parameter efficient fine-tuning. Then comes this MTLoRA, which is a low rank adaptation approach for efficient multitask learning. So in technical terms, MTLoRA is a low rank adaptation approach for parameter efficient fine tuning of multitask learning models, and it aims to facilitate efficient fine tuning in scenarios involving simultaneous learning of multiple tasks from shared backbone network. And this technique utilizes task agnostic and task specific low rank factorization modules for separating shared and task specific parameters respectively. And by doing so, this MTLoRA minimizes the negative effects of conflicting gradients during optimization, thereby reducing overfitting and increasing accuracy in individual tasks with fewer updated parameters than traditional fine-tuning methods. And furthermore, this MTLoRA introduces low rank adaptation in merge operations commonly employed in vision transformer architectures, achieving additional gains in accuracy, efficiency trade-offs during fine-tuning. So in simple terms, imagine you want to teach your AI system to recognize multiple things simultaneously. Example, cat, dog, car from a single image. So instead of creating separate neural network for each task, MTLoRA allows us to share features learned through a base layer before splitting off task-specific modifications to achieve optimal results with fewer updates during retraining. So by breaking down the parameter into generalized and specified features, MTLoRA promotes better collaboration between the tasks and require fewer computational resources, which makes it ideal for real-world applications such as resource-constrained edge devices. Then comes the adversarial low-rank adaptation of vision language models. So this adversarial low-rank adaptation of vision language models is a technique that aims to make vision language models more robust against adversarial attacks by combining low-rank matrix vectorization with adversarial training. So let me explain this in simple terms with an example. Imagine you have a picture of cat sitting on a mat. So a vision language model will try to match this image with text describing it, that is a cat sleeping on green mat, through a process known as embedding. Now this embedding will convert pictures and words into numerical values that computer can process, but sometimes attackers add small changes to the image called adversarial perturbations to trick the models into thinking there is something else in the photo, say a dog. So this is where this adversarial LoRA steps in. So first, adversarial LoRA uses a low-rank matrix vectorization to compress the original high-dimensional matrix containing all the embeddings into three lower dimensional matrices. And each matrix represents either the image features, word features, or the interaction between the two. Since we are now working with reduced dimensions, the resulting matrix multiplication becomes cheaper, faster, and takes up less space, which saves most of the resources. Secondly, during the training phase, we add some adversarial perturbations to the images before passing them through the network. So as the model trains itself repeatedly with perturbed images, it starts recognizing patterns within the noise and gradually gets better at distinguishing real cats from the fake cats. And after this step, the model should perform well even if faced with a similar adversarial perturbations in future situation. So in summary, this adversarial LoRA achieves better performance by optimally reducing the size of matrices involved while retraining model efficacy via adversarial training, thus delivering better efficiency and robustness to LoRA based vision language models. So what's the difference between this LoRA, DoRA, MTLoRA and adversarial LoRA? So first comes this low rank adaptation. So as explained earlier, this LoRA will replace densely connected weight matrices in the middle layer of this pre-trained model with factor matrices to reduce computation and memory footprints during fine-tuning. That is, it decomposes a dense weight matrix into several smaller matrices through matrix factorization algorithms to minimize this number of trainable parameters required for adaptation. Then comes this DoRA, or the weight decomposed low rank adaptation. So similar to this LoRA, DoRA will also introduce a low rank parameterization for dense weight matrices to decrease the computational burden and storage capacity needed during fine tuning. However, instead of utilizing factor matrices, DoRA employs a tensor train format to break down high dimensional tensors into the chain of smaller matrices known as tensor cores. Then comes this MTLoRA. So MTL stands for multitask learning, right? So MTLoRA extends the concept of LoRA to support efficient multitask learning, and it involves simultaneously adapting a single model to perform many related tasks at once, which allows the model to learn shared features among tasks. So this MTLoRA will accomplish this by modifying each task corresponding submatrix within the factor matrices, such as each modification affect only relevant task. Then comes this adversarial low rank adaptation. So while this LoRA aims to improve fine-tuning efficiency, this adversarial LoRA addresses a different challenge in vision language modeling. So specifically, this adversarial LoRA will use adversarial regularization to prevent overfitting issues encountered when applying LoRa to the visual components of vision language models. So by introducing an additional loss term and optimizer to constrain the rank of factor matrices, this adversion LoRa ensures the preservation of crucial information from the visual domain while avoiding excessive model complexity. So in summary, while all these techniques aim to increase the effectiveness and efficiency of fine-tuning pre-trained models, their implementation differs based on their unique focuses and objectives. Thank you.